Good morning, everyone. We are Team 1 from the Communications Project class. Today, we present our automated coolant monitoring system for machining workshops, developed using IoT technology. This project was born from a real need in an industrial workshop with more than 25 machines.
The main problem was the measures were done manually. The refractometer was calibrated. Operators sometimes invented data in the reports, and a single refill mixture was used for all machines. This caused for part oxidations, premature drill wear, and coolant waste. Everything was recorded on paper, with no reliable history. Our solution is justified technically and economically. It provides objective, continuous data, remote access, and cloud traceability economically. It costed 3,050 Mexican pesos. Compare the commercial water level meter that cost over to 700 pesos and only measure level, not concentration. Savings in coolant, rework, and tools justify the investment.
Okay, our general objective was to design a monitoring system that provides real-time information about coolant level and concentration. Specific objectives include measure level with an ultrasonic sensor, correlating that level with concentration using a calibration curve, sending data to Firebase, um, visualizing it on a dashboard with historical graphs and dynamically calculating how much water and how much concentrate to add to reach the ideal measure. Okay, the system architecture is simple but complex. The HCSR04 ultrasonic sensor measures the distance to the coolant surface. The ASP32 calculates the level and estimates the concentration using a calibration curve. Every 5 seconds, it sends the data to the Firebase, a cloud database. The web dashboard updates automatically and show the information to the operation who else receive a recommendation of how much water and how much concentrate to add. Everything is automatic and in real time.
The hardware includes an ESP32 as terrain and HCSR04 sensor for distance measurement and voltage divider because the sensor works at 5 volt while the ESP32 is 3.3 volt. We also added protections, series resistors, parallel capacitors, two ground and TVEs, diodes to filter noise and protect against voltage spikes. We designed and manufactured our own PCB, Intel and Tanya designed and 3D printed a protective enclosure. Everything is integrated into single module. The software calculates level and concentration and every 5 seconds sends the data to Firebase. It connects to Firebase in real time and shows tank level, concentration in degrees bricks, historical graphs, and dynamic recommendation how many liters of concentration to have to reach the ideal for bricks concentration and fill the tank.
Calibrating was done using ultra-cool music. Coolant and rotometer we record the leaking height and concentrate time. We would calibrating curve and programmed and function into the ASP to allow use to estimate the concentration and any level.
The results were positive. We achieved a nice level and concentration accuracy. The system ran without failure for more than 10 hours in laboratory tests, and the dashboard updates instantly. This validates that our system estimates concentration with sufficient accuracy for workshop control. We acknowledge current limitations like lack of protection against motor noise. The database and web page are of public access. The page runs only locally, and we only tested it in lab, not in a real workshop. For the future, we propose adding a temperature sensor, Telegram or WhatsApp notifications, and an automated mixing system with dosing pumps, machine learning to predict consumption, and, and an IP65 hermetic enclosure to protect the electronics. So let me show a brief demonstration of the system in operation. On the screen, you can see the sensor submerged on a container with coolant. The dashboard updates in real time, showing level, concentration, and the mix recommendation. And if I change the level or concentration, the recommendation adjusts instantly. The historical graphs also updates with every new reading. This demonstrates that the system is fully functional and ready to test in a real environment. Good afternoon, everyone. Now we will do the live demonstration of the function of our system, our project. For the demonstration, we will do the following procedure. First, here in this bucket, we have a solution of mixed water with coolant that is actually is currently at 3 bricks degrees. What we will do is to add 1 liter of water, then we will mix the mixture. We will read the concentration with the refractometer, and then we will apply the monitoring system that we will read the concentration, and it will be shown in the web page. So let's go ahead. I will take a liter of water. I will add it to the bucket. I will mix it. I need to mix it carefully to evite to avoid spills. Now I will do the bricks reading. And I will apply the monitoring system. So in the refractometer, we have a concentration of approximately 3 degrees. I will try to show you the reading in the refractometer. And now I will show you the reading in the web page. As we can see, it indicates us the tank level and the estimated concentration. It adjusts dynamically as the SP program sends the information every 5 seconds. And here we can see the recommended mixture. If we want to if we wanted to refill the full tank at a 4 degrees concentration. Now I will show you the historical graphs. Here we have the readings of the last 24 hours that is not actualized because it has been recently turned on. Here we have the readings of the last 7 days, the last 30 days, and here we have the complete historical graph. As we can see, we have timestamps and we have the levels of the tank. This is the water level, the tank level. And here below we have one more time the timestamps stamps, and the historical readings of the concentration. Like here, then it drops as we refill with water. So that's our project. Thank you very much for your. So, in conclusions, the project meets its objectives. We have a functional, low-cost, and replicable system.
Inferring concentration from level simplified the hardware and reduced costs.
The identified limitations mark a clear path for the next stages of the project.
This is the first step toward full automation of coolant control in the workshop. Thank, thank you for your attention.